Hello dear students, welcome to the fourth session. In this session we will continue our discussion about periodic table. We will start with the discussion of typical elements. Now if you can see here, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine. Now these elements are also known as typical elements. They are known as typical element as they decide their own property of the group. That means these elements, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, they decide the property of the element placed below them. Group 1 property. Here group 1 property is decided by sodium. That means whichever property is exhibited by sodium will be exhibited by group 1 element. Group 2 element property is decided by magnesium. Group 13 element property is decided by aluminium. Group 14 element property is decided by silicon. Group 15 element property is decided by phosphorus. And group 16 property is decided by sulfur. And group 17 is decided by chlorine. Now group 18, we all know it is a noble gas, so they are stable. So they have their own property which is stable, having zero valency. The element mentioned, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, they are the hero of their own group and they belong to the period tree. And the group number decides the valency of the element present in their respective groups. Here the group number is 1. So the valency of this entire elements will be 1. This is group 2. So the valency of this entire elements will be 2. Now what is valency? Valency is the outermost electron present in the shell, and this outermost electron decides how it will combine with other elements to attain stability. Now for group 1 and 2, depending on the number of groups, it decides the valency. For group 1, the valency is 1. For group 2, valency is 2. Now when we come to group 13, the valency will be 10 plus valence electron. That means here the valency is 3, 4, 5, 6, 7 in this way. If you are getting confused with the valency of group 13 to 17, just remember the last number. Valency of this group will be 3, valency of this group will be 4, valency of this group will be 5, valency of this group will be 6, valency of this group will be 7, and we know the valency of this group 18, since it is a noble gas, it is 0. So the valencies are 1, 2, 3, 4, 5, 6, 7 and 0. We don't talk about these elements. We hardly talk about D elements for now. We will be only talking about S, P and F also. So far we have learned that the group number present here, that is 1, 2, 13, 14, 15, 16, 17, it decides the valence electron or their valencies. Now period. This period also decide the number of shell. Don't get confused. The group number decides their valency and the period decide the number of shell. For first period, don't get confused. Group means this way, period means this way. So the first period will have 1 shell, second period will have 2 shell, third period will have 3 shell, fourth period will have 4 shell, 5th period will have 5 shell, 6th period will have 6 shell, 7th period will have 7 shell. Now how will they have 7 shells or 1 or 2 shells? Let us see some examples. Taking examples of some of the elements from period 1, 2 and 3, we know that K, L, M and shells. In K shell, 2 electrons can be accommodated. In L shell 8, M shell 18, N shell 32. In your higher classes, you will learn electronic configuration through orbitals 1s, 2s, 2p. We will not discuss about this. we will only discuss about K, L, M and shell. So in first period we have only two elements, that is hydrogen and helium. How many electrons does hydrogen have? 1. So this 1 electron will be accommodated in K shell. In helium there are 2 electrons, so these 2 electrons will be accommodated in K shell, because in K shell maximum 2 electrons can be accommodated. So period 1 means it will have only 1 shell. So we can see that it has only 1 shell, that is K shell. Now in period 2, we'll take some of the elements, lithium, beryllium, boron, carbon. Lithium electronic configuration will be KL, because how many electrons are there in lithium? 3 electrons. So in K shell, 2 electrons can go. This is the maximum number of electrons that can be accommodated in K shell. That is why we are putting only 2 electrons in K shell, so we need L shell as well. So in L shell, 1 electron will go, total 3 electrons. For beryllium, we have 4 electrons. That means atomic number means number of electrons we are talking about. So it has 4 electrons. So 4 electrons will be accommodated in K and L shell, 2 electrons each. For boron, it has 5 electrons. So 5 electrons will be accommodated in K and L shell, 2 electrons, 3 electrons. Carbon 6, so it will be accommodated in 2 shells, K and L. So here we can see that number of period means, for 1 period means 1 shell, 2 period means 2 shell, 3 period means 3 shell. So number of period will decide the number of shell. Number of group decided the valency. Number of period will decide the number of shell. For sodium it has 11 electrons. For magnesium it has 12. So 11 electrons will be accommodated in K, L, M shell. L can accommodate up to 8 electrons. So the remaining electrons go to the M shell. So from here we can know that the period number will decide the number of shell for the elements. Diatomic size increases on moving down the group and atomic size decreases on moving left to right the period. Once again, atomic size increases on moving down the group and atomic size decreases on moving from left to right in a period. Why does this happen? We see that the number of atoms are increasing. These are the electrons. Remember that number of proton is equal to number of electrons. So when we are talking about proton or electron, we are talking about the same thing. So don't get confused. So when we move down the group, what is happening is the period number is increasing. 1, 2, 3, 4, 5, 6, 7. And we have already discussed that the number of the period decide how many shells are present. So for 1, it has only 1 shell. For 2, it has 2 shells. For 3, it will have 3 shells. For 4, it will have 4 shells. That means what is happening in each case? The distance from the center to the outermost shell. Now let us see the trend in the modern periodic table. We have already discussed about valency. Now let us discuss about atomic size. What is atomic size? Atomic size is governed by the distance between the center of the circle to the outermost shell. Now when the number of shell increases, that means the distance will increase, so the atomic size will increase. Atomic size increases with increase in the number of shell. How is atomic size governed? Atomic size is governed by the center of the circle to the outermost shell. Lesser the number of shell, lesser will be the atomic size. More the number of shell, more will be the size of the atom. Now, when we see the periodic table, the distance is increasing in each case. So we can say that the size is increasing. And when the size increases, what happens is this is the nucleus and this is the outermost electron. So there will be less attraction. More the size of the shell, lesser will be the attraction between the nucleus and the outermost electron. Now, what is this called? Diatomic size increases on moving down the group and atomic size decreases on moving left to right the period. Once again, atomic size increases on moving down the group and atomic size decreases on moving from left to right in a period. Why does this happen? We see that the number of atoms are increasing. These are the electrons. Remember that number of proton is equal to number of electrons. So when we are talking about proton or electron, we are talking about the same thing. So don't get confused. So when we move down the group, what is happening is the period number is increasing. 1, 2, 3, 4, 5, 6, 7. And we have already discussed that the number of the period decide how many shells are present. So for 1, it has only 1 shell. For 2, it has 2 shells. For 3, it will have 3 shells. For 4, it will have 4 shells. That means what is happening in each case? The distance from the center to the outermost shell. Now, upon increasing of the shell, the effective nuclear charge acting on the outermost electron also decreases. Now, what does this effective nuclear charge means? Upon increasing of the shell, the attraction between the nucleus and the outermost electron will decrease. That is the decrease in the effective nuclear charge. So, on moving down the group, the size increases and the effective nuclear charge decreases. But when we move from left to right in a period, for period 3, all of them will have only 3 shells, but we see that the number of electrons are increasing. Number of electrons are increasing means, suppose this is the nucleus, 1, 2, 3 shells, because it is the third period. Now for the last 18, for argon 18, suppose we have 1, 2, 3, 4, 5 outermost electron. This is just example. You can check the electronic configuration later. Suppose we have 5 electrons. Here we have 4. Here we have 2. So number of electrons have increased. That means the attraction will also increase. There will be more effective nuclear charge. So upon moving from left to right, the size will decrease because there will be more attraction from the outermost electron towards the nucleus. We see that the shell will remain only 3 for third period. 1, 2, 3, 4. For all these 8 elements, there will be only 3 shells, but the number of electrons will increase. Upon increasing of the number of electrons, the effective nuclear charge will increase and the size will decrease. Now remember that from going from top to bottom in a group, the size increases, but when we move from left to right in a period, the size will decrease, and we are talking about atomic sizes. I have also explained about the metallic and non-metallic character. The left hand side, the light green that you see, they are all metals. The pink one, it is metalloid, and the light yellow, it is non-metal. So when we move from left to right in a period, the metallic character decreases and non-metallic character increases. That means if we start moving from here, they are all metals, but when we reach to the last, it is non-metal. So from moving from left to right, the metallic character decreases and we find non-metal. And this pink that you see, metalloid, it is exhibiting both metallic and non-metallic character. That is why it is known as metalloid. So with this, we come to end of discussion for chapter 5, and you also watch the video attached for more clarification. If you have doubt, you can always approach me.
Let's take a look at group trends first. As you travel down a group, you are adding electrons to energy levels that are farther away from the nucleus. All elements in group 1 have one valence electron, but different electron configurations based on their period. Hydrogen is in the first period, which means it has one electron shell. Its atomic number is 1, which means a neutral atom of hydrogen has one electron. Lithium is in period 2, which means it has 2 electron shells. Its atomic number is 3, so a neutral lithium ions configuration looks like this. Sodium has 3 electron shells. Its atomic number is 11, so a neutral atom has 11 electrons. As you continue down the group, the atomic radius continues to increase due to the increase in electron shells. Now let's examine trends across periods. As you are traveling across a period from left to right, the atomic radius decreases due to the effective nuclear charge and electron shielding. We're going to compare lithium and beryllium to gain a better understanding of how these processes affect atomic radius. Lithium has an atomic number of 3. This means a neutral atom of lithium will have 3 protons and 3 electrons. There are 2 electrons in the inner shell and 1 in the outer shell. The positively charged protons pull in the negatively charged electrons. At the same time, the inner shell electrons repel the outer shell electrons because they have the same charge. This is called electron shielding. When we move from lithium to beryllium, we gain 1 proton and 1 electron. It's important to note that outer shell electrons do not shield the other electrons. That means that beryllium has the same number of electrons shielding as lithium does. However, beryllium does have a higher effective nuclear charge because of that additional proton. This increased positive charge in the nucleus causes electrons to be pulled in more strongly, resulting in a smaller atomic radius. So as you continue to travel across the period, the atomic radius continues to decrease.